So in this video, we're going to talk about trigonometric substitution. And in this video, we're actually going to do the trig substitution themselves, okay? And so let's look at a couple easy ones first, okay? So what if we wanted to take the integral of 1 over 1 plus x squared dx, okay? Actually, we know the integral of this. This is tangent inverse of x, but how do we do the antiderivative? Well, we got to use trig substitution. And to me, it looks as if the identity I will use in this case is 1 plus tangent squared of theta, and that is equal to secant squared of theta. Okay, I have a 1 here, so there's no need to change any coefficients in my identity. And so I know tangent squared of theta maps to x squared, so we could set them equal to each other. Okay, if I take the square root of x on both sides, then I get x is equal to tangent of theta. So this is what I'll substitute. Now I have x, I need to find what dx is. And so if I take my derivative of tangent of theta is secant squared of theta. And so now that I have everything, I could set this to be 1 times dx, which is secant squared of theta. Okay, and we're going to divide that by 1 plus, well, what x squared is tangent squared of theta. Okay. And this is a d theta, so I forgot my d theta here, okay? And so the new integral becomes like this. And so if I look at this, well, this becomes secant squared of theta, d theta, times, well, I'm always going to look for identities in the denominator. And so 1 plus tangent squared of theta is actually secant squared of theta. Okay, and you can see now that I have secant squared of theta on both sides, both ends, so I could divide those and cancel those out. So my new integral becomes 1 d theta. I know the integral of 1 in this case will be theta plus c. Okay, now the idea is, what is theta? Well, always go back to your term x is equal to some. Always go to what you'll substitute, what you did substitute in for x. And here's a rationale. If x is equal to tangent of theta, then theta must be equal to tangent inverse of x. Okay, so all I'm doing is taking the inverse to get what theta is actually equal to. Okay, essentially, if you look at this, well, tangent inverse of tangent is actually just they just cancel out to give you 1, and then we have tangent inverse of x on both sides. So we're just literally taking the tangent inverse on both sides. And so if we replace theta with tangent inverse of x, then we could see that our integral actually tangent inverse of x plus c. Okay, so let's look at one more simple one, and let's go deep down into what really trig substitutions are. So what if we wanted to integrate the idea of this here, 1 minus x squared? Okay, well, to me it looks as if I have some sort of cosine here. You see that the identity in this case would be 1 minus cosine squared of theta is equal to sine squared of theta. And again, you could actually use cosine too. You could say 1 minus sine squared of theta is equal to cosine squared of theta. Either or works. Okay. Sorry. And so if I look at this, well, because this is 1, I literally have to change nothing in my identity. And so we know that cosine squared of theta maps to x squared. And so if that is true, then we could set them equal to each other. And so taking the squared on both sides, I get x to be cosine of theta. Okay, now I have x. I need to find what dx is. So if I take my derivative of cosine of theta is actually a negative sine of theta, d theta. Okay, and so now that I have dx and x, I could just rewrite my integral. What's dx? That is negative sine of theta, d theta. I still have the square root here of 1 minus, well, what's x squared? That happens to be cosine squared of theta. Okay, so there goes my new integral. And now I'm always going to look for identity. So we said this is equal to negative sine of theta, d theta, divided by the square root. Well, 1 minus cosine squared of theta, that happens to be sine squared of theta. Well, again, notice that if I take, I'm going to just factor out my negative here. So this becomes negative times the integral of sine of theta d theta divided by, well, what's sine squared raised to the 1/2 power? Well, if I multiply those, that will give me 1. So therefore, this is just sine of theta. And another way of saying that is that square root of sine squared of theta is just sine of theta. Okay, notice that I have both on the numerator and denominator, so I could just cancel. This becomes 1. And so my integral looks to be negative the integral of 1 d theta. We know the integral of 1, that happens to be negative theta, okay, plus c. So we just carry our negative. Integral of 1 is just theta, and we still have our negative here plus c, okay? Now again, what did I substitute in for x? X is equal to cosine of theta. And so if x is equal to cosine of theta, then theta must be cosine inverse of x. And so we know the integral in this case would be negative cosine inverse of x plus c. Okay. So now that we've covered some of the basic integrations, let's look at something a little bit more challenging. So, what if, let's see. So what if we're given an integral here where we have dx over 4 plus x squared, okay, and this is a square root of 4 plus x squared. How do we solve this one? Well, to me, it looks as if I have some sort of tangent here. I have some number plus tangent square root of theta, and that is equal to secant square root of theta. So we have tangent square root of theta plus 1, and that is equal to secant square root of theta, okay? Well, to me, I don't have 1, I have 4, and so if I replace everything with 4, the coefficient of 4 inside, then now I can see that 4 tangent square root of theta maps to x squared. And so if that is true, we set them equal to each other. So this becomes 4 tangent square root of theta. And so if I take my square root on both sides, x becomes 2 tangent of theta, because the square root of 4 is just 2. Square root of tangent squared is just tangent. Okay. And now that I have x, I need to figure out what dx is. Okay. And so if I take my derivative, well, this becomes 2. What's the derivative of tangent? That becomes secant square root of theta. Okay. And so now that I have everything on top intact, I could just go ahead and do my integral. So if I rewrite my integral, this becomes the integral of dx, which is 2 secant square root of theta. And we're going to divide that by the square root of 4 plus, we're going to divide that by the square root of 4 plus, well, what was my x squared? That happens to be 4 tangent square root of theta. 4 tangent square root of theta. Okay. And so if I look at this, well, this becomes 2 secant square root of theta. And what I'm going to do is factor out of 4 here. Okay. So if I factor out of 4, this becomes 4 times 1 plus tangent square root of theta. And I forgot my d theta here. I'm sorry about that, guys. Okay. Dx, derivative of 2 tangent square root of theta is just 2 secant square root of theta d theta. Okay, so I forgot that. Otherwise, the integral does not make any sense. Okay. And so now that we're in this form, now I see a pattern here. Okay. So if I look at this, this is equal to the integral of, well, if I factor out my 2, this becomes secant square root of theta d theta. And we're going to divide that by, well, look, this is an identity. 1 plus tangent square root of theta is secant square root of theta. Secant square root of theta. And we have a 4 here, and this is a square root. Okay. So notice I keep my 4 and just replace this with the identity. And so if I look at this, this becomes 2 times the integral of secant square root of theta d theta. And we're going to divide that by, well, if I take the square root of 4, that becomes 2. If I take the square root of secant square root of theta, that becomes secant of theta. Okay. And so now we're in a solution like this. Now, hopefully you could see that this is a 1/2. So if I factor it out, this will actually cancel out. Okay, so the 2 on the bottom and 2 on the top cancel out. Okay, and then notice that I have 1 secant here. So this is equal to 1. And if I take out 1 here, I still have an extra secant of theta. Okay, so if I look at this, this is now the integral of secant of theta d theta. Okay. Now we actually know how to integrate this. Okay, we know how to integrate this. So how we do this is that this is now equal to the integral of secant of theta times secant of theta plus tangent of theta on both sides, secant of theta plus tangent of theta d theta. Okay, so this is how we integrate this. Okay, and essentially when we factor it out, we use u substitution. And so the idea is this is now equal to the integral of secant squared of theta plus secant of theta tangent of theta d theta divided by secant of theta plus tangent of theta. Okay. And the idea is now we could use u substitution. So if I set u to be secant of theta plus tangent of theta, which is on the bottom, then the derivative is actually everything on the top. So derivative secant of theta is just secant of theta tangent of theta plus, well, what's the derivative of secant? No. What's the derivative of tangent of theta? That is secant squared of theta. Okay, and so essentially we did this as our u, and we got the top. And the derivative of secant of theta d theta. Okay, so derivative is secant of theta tangent of theta plus secant squared of theta d theta. Okay, so we got everything on the top here. And so if I look at this now, my integral is now written as 1 over u du. Okay, and du replaces all of this. And here's our u. Okay, so if we look at this, this becomes now the integral. We know 1 over u, that becomes a natural log of the absolute value of u in this case, which was secant of theta plus tangent of theta. So this becomes natural log of secant of theta plus tangent of theta plus c. Okay, now in this case we're not done it. Okay, so there's our integral. Now some teachers actually will allow you to stop here. I'm not quite sure, but that's not the fully complete integral. We need to get everything in terms of x. Okay, and so if I look at this now, my integral is actually now will be given by the natural log of, well, let's look. Well, what is theta? We need to find what theta is. And so if we look up here, look at what we substituted. Okay, x is equal to 2 tangent of theta. Okay, and so here's the rationale. If x is equal to 2 tangent of theta, then we need to find what theta is. So if I divide by 2 on both sides, well, x over 2, this is a 2, x over 2 is equal to tangent of theta. So therefore, if I take the tangent inverse on both sides, then I get theta to be equal to tangent inverse of x over 2. Okay, so this is what we substitute in for theta. And so if I look at this now, this becomes a natural log. Let me kind of make sure you can see. So this becomes a natural log of secant. Well, what is theta? That is tangent inverse of x over 2. And we're going to add that to tangent of, well, what's theta? Again, theta is tangent inverse of x over 2 plus c. Now, so this is not complete. This is where some teachers will actually let you stop. Okay, now I'm not going to stop there. I'm going to simplify a little bit more. Okay, we got to get everything down in terms of just pure x. And so what I usually do for this part is set up a triangle. Now, for your info, if you did not know, tangent of tangent inverse, those cancel out. Okay, and it's the same thing. Cosine of cosine inverse, sine of sine inverse, those will always cancel out to just give me x over 2. But what is this one? Okay, and so what I usually do is set up a triangle. So if I look at this, I set up a triangle. I always put theta in this corner here. And here's what this question is asking. This question tells you that tangent of the angle is x over 2. And so if I look at theta from this part, well, what is tangent? Tangent is opposite over adjacent. So, or x will actually be opposite on the top and adjacent would be bottom. So this will be 2. So this would be x over 2. So here's tangent of the angle. Okay. And essentially what they're asking you to find is what is secant of this angle. Okay, so you write, so they give you tangent of the angle and they're asking, well, what is secant of the angle? Well, whenever it's like this, I always want to find my hypotenuse. Okay, and we know this is the Pythagorean theorem, and We say the hypotenuse is always given by the addition of these two, the square root. So the hypotenuse in this case is just x squared plus, well, what is 2 squared? 4. Okay. So in case you don't know the Pythagorean theorem, go ahead and revisit that. But again, hopefully you can see that the idea is tangent of this angle is x over 2. Well, x on the opposite side, 2 on the bottom. And basically I'm finding the hypotenuse. Well, the hypotenuse is just squaring those two. I'm going to take the square root. I'm going to add those together and square them. So this becomes x squared plus 2 squared, which is 4. And so I'm going to leave it like that. I'm not going to try to simplify, okay? And so now that we find the hypotenuse, then I'm saying to myself, what is secant of theta? Well, we know we know cosine is related with secant. Cosine is related to secant. Okay, and how are they related? We know that if we find cosine of the angle, the opposite is true. If I just flip those, I'll get secant. And so cosine of this angle is adjacent over hypotenuse. So cosine of theta is adjacent over hypotenuse. So this becomes 2 over the square root of x squared plus 4. And so we know that secant is a reciprocal. So secant of this angle is actually the square root of x squared plus 4 over 2. And so essentially this is now what I'm plugging in for this whole term here. So my integral in terms of full x is actually given by the natural log of the absolute value of the square root of x squared plus 4 divided by 2 plus, well, tangent inverse of tangent inverse, those would actually cancel out to 1. So this becomes x over 2 plus c. And there's my complete integration. Now, again, some teachers will allow you to stop here. Again, but some teachers, I knew when I took this class, teacher exactly wanted this rationale here. So hopefully this makes sense.